Hello everyone. In today's video lecture, I am here to explain about subsurface sounding method of soil investigation. This method is generally used for determining the consistency of cohesive soils or relative density of cohesionless soils. Procedure involved: the rod encased in a sleeve is forced into the soil and the resistance to penetration or withdrawal is observed. Variation in this resistance shows dissimilar soil layers. The advantages of subsurface sounding methods are: it is faster and cheaper than boring method. It can be used in erratic soil conditions. The disadvantages or limitations involves: it gives no idea about the settlement characteristics of soil. This method alone cannot provide sufficient data for the final design purpose. Various methods of subsurface sounding are as follows. First is standard penetration test. Next one is cone penetration test or Dutch cone test. The most commonly method used in world widely are standard penetration test. SPT in short is a common in situ testing method used to determine the geotechnical engineering properties of subsurface soils. This test is carried out in a borehole. This test will measure the resistance of soil strata to the penetration undergone. A penetration empirical correlation is derived between the soil properties and penetration resistance of the soil. The test is extremely useful for determining the relative density and the angle of shearing resistance of cohesionless soils. This method can also be used to determine the unconfined compressive strength of cohesive soils also. The tools required for standard penetration test are a standard split spoon sampler, a drop hammer weighing 63.5 kilograms, guiding rod, drilling rig, and the driving head anvil. This is a pictorial representation of a standard penetration test where a hammer or a drop weight of 63.5 kilograms is dropped from a height of 75 centimeters with the sampler being connected at the bottom end. The sampler consisting of cutting edge at the bottom. The most commonly used sampler is split spoon sampler. The 63.5 kilogram mass is lifted by means of pulley and made to drop with a free fall of 760 millimeter or 76 centimeter. This is a pictorial representation of standard penetration test. The procedure involved in this test is: a test is conducted in a borehole by means of standard split spoon sampler. Once the drilling is done to a desired depth, the drilling tool is removed and the sampler is placed inside the borehole. By means of drop hammer of 63.5 kilogram mass falling through height of 750 millimeters at a rate of 30 blows per minute, the sampler is driven into the soil. The number of blows of hammer required to drive a depth of 150 mm is counted. Further is driven by 150 mm and the blows are counted. Similarly, a sampler is once again further driven to a depth of 150 millimeters and the number of blows is recorded. The number of blows recorded for the first 150 mm are not taken into consideration as it is a seating drive. The number of blows recorded for the last two 150 mm intervals are added to give the standard penetration number. The standard penetration number N is the number of blows required for 150 mm penetration beyond a seating drive of 150 mm. If the number of blows for 150 mm drive exceeds 50, it is taken as a refusal and the test is discontinued. The standard penetration number is corrected for dilatancy correction and overburden pressure correction. Before the SPT values are used for empirical correlation and design charts, the field N value have to be corrected as per IS code 2131-1981. The two corrections involved in standard penetration test are: first one is dilatancy correction. This correction is especially made for silty fine sands and fine sands below the water table, which develops a pore water pressure which is not easily dissipated. The pore pressure increases the resistance of soil and hence penetration number. Terzaghi and Peck in 1967 recommended the following correction in case of silty fine sands when observed value exceeds 15. So if the observed value only exceeds 15, dilatancy correction to be made. So corrected N value is equal to 15 plus half of observed N value minus 15. So N is the corrected N value for overburden effect and capital N is the actual value of blows. Next is overburden pressure correction. From several investigations, it is proven that the penetration resistance or the N value is dependent on the overburden pressure. If there are two granular soils with relative density same, higher N value will be shown by the soil having higher confining pressure. With increase in depth of the soil, the confining pressure also increases. So the value of N at shallow depth and larger depths are underestimated and overestimated respectively. So correction for overburden are as follows. For overburden pressure less than 75 kPa, the following correction is adopted. N dash is equal to 4N divided by 1 plus 0.04 P naught. For overburden pressure greater than 75 kPa, N dash is equal to 4N divided by 3.25 plus 0.01 P naught, where N dash is the corrected N value, N is the observed N value, P naught is the overburden pressure. Overburden pressure can be calculated by multiplying the unit weight of soil by the depth of the soil profile which is to be considered, where D is the depth of testing. Gamma is the unit weight of soil at the time of testing. I hope this video is useful to you as it explained about various methods of soil exploration, especially standard penetration test method of soil investigation. Thank you everyone. Have a good day.